Hey everybody, this is Mark Mays with OutBack Power, and I'm going to be doing the webinar today on battery charging best practices. And with me today is Roy Dingen, our illustrious certified training program instructor, amongst other great things that he does.
Good morning.
And so Roy and I are going to be tag teaming the webinar this week. My voice has been struggling with a little bit of a head cold this week, so it may not last. So I'm going to probably be doing the first part of the webinar and maybe some at the end, and Roy will be handling the middle section. So and then at the end we will be taking questions at the end. So if you have your questions, feel free to go ahead and type them in as they come to mind, and then we'll address them at the end of the webinar. This probably will be a full 60 minutes, we're estimating. Hopefully there's some good information that everybody's going to benefit from. So that said, we'll go ahead and get started. Okay, so the webinar today, we're going to talk about some battery terminology. One of the things is even though we understand some of the terms, we want to put a little bit of meaning behind those terms, how they affect battery performance, maybe give you some information that will help you choose the best battery for the application. Roy's going to talk about three-stage charging, how battery settings affect longevity performance. We'll talk a little about state of charge, and then finally we're going to end with battery commissioning and tips and precautions. Okay, so under terminology, days of autonomy is probably one of the most dangerous questions you can ask your site owner as an installer. If you ask them just wide open, well, how many days of autonomy would you like? The common answer is 2 weeks or a few days or whatever. And the thing to keep in mind, days of autonomy affects the size of your battery bank. For example, the most efficient system is a 24-hour 1 day of autonomy system, as it kind of follows the sun cycle. And if you were to add a second day of autonomy, you're basically doubling the size of your battery bank. So anyway, days of autonomy are the number of days the batteries will run loads without recharging. Cycle is simply just one charge and discharge cycle. Even if it doesn't fully charge or fully discharge, it's still counted as one cycle. When the charging ends and the discharging begins, that's a cycle. SOC also, which is state of charge, and DOD, depth of discharge, you can see that they are the opposite of each other. So if I've used a 10, if I only have 20% capacity in my battery bank, that's a 20% state of charge, and which means I've taken it down to 80% discharge. So they're just inverse of each other. What affects battery capacity? This is really important to know and understand, especially if you're in places that a battery bank is not in a controlled ambient environment, and you do see some extremes in either cold or heat that will affect. So for example, if you're in a cold climate, then it's going to reduce the capacity of the battery. And likewise, on hot temperature, the battery cycle life is going to be reduced. Now, we do have ways of mitigating the effects of temperature with temperature compensated charging, and we'll talk a little bit more about that at the end of the session here. But this is definitely a trade-off. We do have a sizing tool for helping you size a battery bank to a given set of load profile. In there, you do have the option of sizing your battery bank according to expected ambient temperature. Depth of discharge versus cycles. So if we're only going to discharge our batteries 20%, we might see as many as 3,300 cycles over the life of the battery, versus if we were going to discharge it more deeply, down to 80%, that's going to significantly reduce the cycle life. One thing to point out is, Roy likes to point out, is the available energy is pretty close to each other. You know the total energy over the life of the battery. It's just whether you're going to use a little bit of a time or a lot more of it in a shorter period of time. So this is the trade-off that you'll need to make with your site owner of cost versus the type of application. And we're going to talk more about what batteries fit better in different applications later as well. So another important thing to know is rate of discharge. As the rate of discharge goes up, in other words, if we discharge a battery in a shorter amount of time, then the capacity always will go down as well. So when we discharge it faster, the capacity is going to go down. So here's an example. We have our EnergyCell RE batteries, our EnergyCell GH, our pure lead batteries. And if we look at the 100-hour discharge rate on this row, we can see that they're the same at the 100-hour rate. But as we go down, and the faster discharge rates, like down to the 1 hour, we can see there's about a 15, maybe 70% difference in capacity of one battery type towards another. And these are both AGM batteries. So you get variation within battery types, and also you can see when I go from a C100 100-hour discharge rate down to 1 hour, I'm reducing about 50% of my capacity. So even at small, even at not quite so dramatic discharge rates, we're still seeing a reduction in capacity. So keep that in mind. This also is the same for charging the battery also. The faster we charge the battery, the less capacity it's going to have as well. So other things that can affect battery performance, undersizing a battery bank can result in an overcharge from the PV array. If you've oversized your array, and certainly solar panels are cheaper than batteries at this point in time. Somebody might go a little bit heavy on the PV side of things, but we have to keep in mind that there's the chance that we have too big renewable energy charging source, then that could affect the overcharging the battery. Now, we can always limit the charge controller output, but then we might run the risk of curtailing the PV array. We might be leaving available energy up on the roof if we limit the output of the charge controller. Now, we do have a function in our Mate 3 called Global Charge Control. There's an application note that will be coming out shortly that will explain a little bit more about that. And in a case like that, you can still limit the amount of energy going into the battery bank while still offsetting energy to the loads or to the grid. So, but keep in mind, if you just set that up without compensating for it, you could run the risk of damaging the battery. Now, oversizing the battery bank can undercharge the batteries, and this is one of the things I've seen in like some off-grid systems. People want to make sure that they have enough days of autonomy. They're living off-grid. They don't want to run their generator too much. However, if you oversize the battery, you might be having the opposite desired effect. You actually might be charging more from the grid or the generator because the renewable energy sources aren't enough to keep the batteries charged. And undercharging the batteries can be just as damaging to the batteries as overcharging them. So sizing the battery bank to the load, to the array, is just as important in performance, not just system performance, but actually longevity and performance of the battery. And again, that kind of touches on this, undersizing the battery bank relative to the load. So if your load, if you don't have enough big enough battery bank to really handle the load, even if it's just not an off-grid system, but say you're doing ancillary services like peak shaving or something like this, You can cause deeper and more frequent cycling of the battery, which again can reduce the battery life. And when you do that, then there's less backup power for grid outages. Temperature compensated charging, basically, it's going to enhance the battery life in hot environments. We're going to reduce the charging voltage on the battery the higher it goes. And that's into effect, I think it's up to about 35 degrees C is where that sort of flattens out. It won't continue correcting past 35 degrees C. But it can really significantly affect the battery life in a positive way. Likewise, increases capacity in a cold environment. And what it does that, it actually increases the charging voltage as the temperature goes down, which can help actually increase capacity in there. And one thing to keep in mind also, when a battery does get cold, as long as it's not severely cold, like freezing cold, where the electrolyte might freeze, it actually will recover. So it's not going to do any long-term damage. The main penalty is just less capacity. Okay, so I'm going to go ahead and turn this over to Roy.
Good morning. So, I've heard it said once that there's no such thing as a good or a bad battery, but there are good or bad batteries for application. So, and the ones we're covering, of course, today here are OutBack batteries specifically, but choosing the right battery for your application is as important as sizing the battery correctly. So from an example, to start out with, we have something called, and this is an AGM battery as well, first off, but it's called the OutBack EnergyCell RE battery. The RE stands for renewable energy. And I would call it a cycling battery. There are better options for cycling batteries, but they're not maintenance free, of course. But so for moderate cycling applications. And so we make them in a 12-volt battery. We see there on the upper graphic there is a 12-volt front terminal battery. We'll get into some models, I believe, here, but about 200 amp hours, depending on the model, at the 100-hour rate. Down the bottom right-hand corner, you'll see a 2-volt cell, and they're for larger systems. And the reason, which I don't know how deep we'll get into it here, but we really want to avoid more than 3 strings of batteries, if at all possible. So if you get to a situation where a 12-volt battery is going to end you up with too many strings, we want to go to a lower voltage cell. But that's a good one for like I said, moderate cycling applications. But that's not everybody. If you're in a battery backup situation, and in a battery backup situation, quite frequently the battery is only used once or twice a year, and so it's been asked to do a completely different job, and that job is to be on standby. And so we have what we call our GH batteries. They're the red ones, they're pure lead, and they're really low self-discharge. Voltage set points are all the same. We'll get into what the voltage set points are later, but it's primarily for a float battery. And so we'll see also a graphic of the number of cycles that this battery is capable of, and you'll notice that the number is basically vastly lower than the previous battery when total number of cycles, but that's not what it was designed for. It was designed for being on a backup situation. Its shelf life, if you will, is superior by about 50%. So you'll end up with a battery that lasts 15 years sitting in float waiting to be used versus one that's possibly 10 years. So again, right battery for the application. Another one we have is what we call the nanocarbon. Really similar to the RE, except that there's some additional material on the plates there to kind of protect it from the effects of partial state of charge. So it does better in a partial state of charge application. So if used right, you can get quite a few more cycles out of this battery, treating them a little bit different. There's a paper out on this. We won't go detailed on to how that treatment is, but in a nutshell, you don't want to charge them up as much frequently. So we want to live in a lower side of state of charge range. All the safety and convenience of an AGM, and these are all AGM batteries so far, and they come in a 2-volt or a 12-volt cell as well. One thing I'm going to note here too, that I'm sure there's probably a bunch of hands going up out there saying, oh, what about lithium? What about lithium? Well, that's a completely different technology. What we're talking about here today is going to be all the lead acid technologies only. So we'll just kind of throw that out there. So we also now, fairly recently, have taken on a line of flooded lead-acid batteries, which, you know, are pretty popular in the off-grid world, you know, heavy cycling applications. We have basically three models. One is a 6-volt, 290. Is that a 6-volt or a 12-volt?
6-volt.
It is a 6-volt. I got that right. Okay. It's a 6-volt, 290 amp hour battery. Golf cart size, I would call that, maybe something similar to a T105, basically. And then we have the EnergyCell 525 FLA, which is a similar. It's an L16 size battery, and then all the way up to a 1400 amp hour 2-volt cell for more, you know, for larger systems. Heavy duty internal post and terminal. These are not maintenance free batteries. These are batteries made for off-grid people who know and love their batteries and take care of them. Proprietary plate separators guard against short circuit, deep cycling construction for better performance and longevity, more fluid headspace, which is good because if you run them low on water, of course, we have real bad problems. Electrolyte level indicators on the 525, which is really nice for a smaller battery to be able to basically easily see what their electrolyte level is and when we need to add water. And again, they come in 2 and 6 volt. So back to the float life thing. When I was talking about the GH batteries, I mentioned that some batteries do better when just sitting around, basically waiting to be used, and some batteries don't do so well. And we can see here on from the far right, working left, the far right is a flooded battery sitting in a float application, and we can have an expected shelf life of about 3 years. So if I was doing a battery backup situation, I could use the best flooded lead acid battery in the world, and it really wouldn't be the right battery. So 3-year shelf life, not ideal. Coming to the left a little bit, we got the RE or the NC. Now we got about a 10-year flow life, much better. You know, it's an AGM type battery. It's not an AGM type, it is an AGM battery. It's a quote maintenance-free battery, and it's going to be probably used more in a battery backup application as well because it's maintenance-free. But if we keep working our way to the left, we have the GH, which is at 15 years on the shelf life. So even though you'll see later that the cycle life may not be as good, the shelf life is better, and you'll get more use out of that battery for a battery backup application. One that we don't see here in the States much, and I'm not super familiar with, is the OPZV or OPZV, depending how you say it. And it's a tubular gel, and they've got really good performance characteristics, and their shelf life in particular, we can see here about a 20-year. Now that's at a 20-degree Celsius ambient temperature, so if you keep them a little bit cool, they can really have an extended float life. So you can see that there's you want to look at your batteries, not only the brand, but the model for your particular application. And here we see a chart and this is a chart that you should see on any battery you look at, and this is going to be life cycle or depth of discharge versus number of cycles. And so the lower the number, of course, the worse, quote, the worse the battery is. If we look at the very bottom one there, you'll see that that battery is only going to be capable at a 50% depth of discharge of what, about 700 cycles or so, 500 cycles. No, yeah, something in there, low. So if you're going to be cycling a battery, that's the RE or the GH battery. You wouldn't want to use that at a daily cycling system. It's not going to last you very long. Working our way up, next one up is I can't see the colors. I'm colorblind. Okay, that's the FLAs. So now you can see when you start, those batteries are pretty good, especially if you're not going to discharge very much. They've got a really nice long life in a cycling application. Wait, that's the RE. Okay, so I'll say that's the one I was saying is the moderate cycling capability. Next one up, we see the NC, which this is based on using them correctly and we have a tech note on this on how to charge and discharge them to the proper levels to increase their life cycle. And we can work our way up to flooded lead acid batteries and OPZV batteries again. So you can see the OPZVs really are good both in terms of cycle life and in terms of shelf life. But for the most part, in an off-grid system, I'd probably end up with an FLA, flooded lead acid. In a occasional backup system, I would end up with a GH, but always keep this in mind when you select your battery. And systems that we use these in can be very different. Just because you have a battery connected up to a battery-based inverter doesn't mean it's going to be used the same. Here we see an on-grid system. We can tell that because we have a battery backup load center, or we have a load center there, the backup load center on the left, and we have our main panel on the right going back to the grid. And with that bidirectional arrow, I can see that I'm in a grid tie application, and which would mean that that battery is going to be remaining full and basically just going to be selling back to the grid. So the reality of it is, I would probably, in that case, this might be, depending on their outages, be a good candidate for the GH battery. But you can see how we're using it completely different than in this next system, which is off-grid. Off-grid, we're going to be cycling that battery every day. If the battery is too small, we might be cycling it twice a day. Not a good idea. But we're going to be using them very differently. And we're going to be discharging them and charging them up every day versus the previous slide where we're going to be maintaining them full. So that's kind of, in a nutshell, the differences, primary differences you'll see in applications for a battery-based inverter. Here we have a comparison chart. I won't read all this to you, but these are the flooded lead-acid battery. That's the FLA from left to right. We have the renewable energy series. That's the gray one. We have the nanocarbons, the NC. We have the GH, which that's the pure lead, the red ones. Those are the best for float applications, and the OpticsRE on the right. And the ones that look at closely right now are the bottom four rows. So float life, you can see a vast difference between, say, the GH and the flooded lead acids. So, of course, with 3 years float life, float application is a no-no with a flooded lead acid battery. Cycling applications, we get down here, we can see that a flooded lead acid battery is great, as is the OpticsRE. Price scale, now this is upfront cost. One thing I really like to emphasize here, and I think Mark kind of alluded to my comment on the cycle life versus total number of cycles. What you want to basically do, there's two ways to look at battery cost, and one of them is upfront battery cost. You can just real simply say, here's my cost per amp hour. But if you look at the cycle life and your intended use, and you say at this depth of discharge, I can pull this many kilowatt hours out of that battery and make this many cycles, I can figure out the lifetime kilowatt hour delivery out of that battery. Divide that by the cost, and I come up with a cost per kilowatt hour. So really, when we look at the price, we not only want to look at upfront cost, we want to look at cycle life cost of the battery too. So if you want to go further into that, I would suggest our certificate training program. And it's a 4-day program. I go into totally calculating cycle costs and everything. But for today, we'll just leave it at that. So one of the things that needs to be understood when charging a lead-acid battery, and again, I really say that very specifically, a lead-acid battery, because they're very different than, say, well, I'll just put it for a quick comparison, very different than all the lithium technologies, which we are not going to cover here. And so understanding how this 3-stage charging algorithm works is crucial to understanding what your set points are. In my days in tech support, I remember that the most frequent question asked was basically, how do I charge my batteries? And so understanding that charging algorithm is critical to knowing how this works and getting the set points from your manufacturer. So what we see here is your typical 3-stage charging algorithm. You'll see a blue line and you'll see a red line. The blue line is voltage, the red line is current. And one thing I really like to emphasize here is the blue line is an algorithm that's determined by your charging source, whether that be your inverter, your charge controller, what have you. That is determining that charge voltage and where we are in this algorithm, which I'll cover. The red line is current, and you'll see sort of an algorithm there. You'll see it tapering down as the battery gets fuller and fuller. But that is not determined by the inverter, the charge controller, etc. That is actually determined by the battery itself. And so I'll go through this step by step. For your typical 3-stage, and by the way, there's other stages people will add sometimes. People will say, oh, we have 4-stage charging because we have equalizer, 6-stage charging because we can go silent, or 32-stage charging, or what have you. But it's all variants of 3-stage charging. So the first stage we call bulk. And the bulk cycle, what we're doing is we're climbing up to our voltage. And that can be programmed as an absorbed voltage or as a bulk voltage. In our case, we program an absorbed voltage. So that's a voltage you're going to be wanting to program, absorb. That climb up to it is an indeterminate time period there. It depends on your charging source, your battery size, your capacity of your charger, and other things. So that first stage bulk is indeterminate in time. It's not a time that you program because it just depends on how long it takes to get up there. During that phase, you'll see the current peaks, and it goes up to its maximum, and you'll see it plateauing there. And what we see there is the maximum charge rate of either the inverter or the total wattage or amperage available from our PV array or what have you. But it's our maximum. It goes straight to maximum, wherever that is. And it'll just plateau there because there's no more left to give. Once the voltage reaches the absorbed voltage set point, now the battery is no longer climbing in voltage. And as the battery state of charge goes up, its internal impedance also goes up, which limits the current flow. So now we're going to see that current flow actually taper down on its own. This is a function of a lead-acid battery. This is not the algorithm per se, because we're not climbing in voltage any longer. So you'll see that current taper. So if we look here, well, actually, and then I'll get to the float. So at the end of that cycle, that absorb cycle, and some people actually call it acceptance charging, and I like that one because it's how much current the batteries are going to accept. We then drop into a float charge, depending on whether we're using generator or what have you. We may even turn off the charging algorithm altogether. But what's important is that little box in the bottom right here, battery SOC at a certain point. So at the end of a bulk cycle, we're somewhere between 70 and 90%. So I've talked to customers frequently and say, I got the voltage up to 57.6, and they just go right back down again. They expect them to be full based on voltage alone. That just does not happen. You're only at 100% after you absorb the batteries and after that current has tapered down to about 3% of your total battery capacity. So for instance, on a 100 amp hour battery, that current will taper, and once it hits 3 amps, 3% of 100, we can pretty much determine that battery is full. And then we can make a decision on what to do at that point, either go into float, turn off the charger, depending on what we want to do, shut down the generator, for instance. And these voltages, by the way, are temp compensated, as Mark was talking about earlier, which means that if we program the battery charging voltage, that absorb voltage, or that float voltage to 57.6, for instance, that's based on 25 degrees C. So once that battery goes colder, that voltage goes up a little bit. If it gets hotter, then the battery voltage goes down a little bit. But that is the algorithm in a nutshell. There's many variants on this when you're doing grid type cell, when you're doing different ones. But from just a basic standpoint, there's your 3-stage charging algorithm. So when you're programming an inverter, the primary voltages you're going to be programming are going to be bulk and float. And the bulk, you might find it programmed as absorption voltage. You might find it programmed as bulk voltage. And that's going to just depend on the manufacturer. They are the same. Because remember, bulk is the climb up to the voltage, absorb is the point of holding it there. So the two primary voltages you're going to set are either bulk or absorption, depending on the manufacturer. I don't even remember what we do.
Absorb.
Oh, we do absorb. Okay.
Some battery manufacturers even call absorb equalize.
Correct.
Which is different.
That's completely different, yeah. And then we have float. So those are the two primary ones, and then two equalize. I don't know how, will we go into equalize here?
We'll touch on it.
Okay, I'll get to equalize one. I'll get to that later. Then I won't go into that right now. But those are the primary ones you're programming, and those voltages always come from your battery manufacturer. So in the case of our batteries, yes, that's us. We call our tech support. We put stickers on the batteries. We have tech notes. There's actually a screenshot here you'll get. It's got all the voltages. We make it very easy to find these voltages. Some manufacturers don't. I've always said, if your battery manufacturer tells you to call the inverter manufacturer to get the voltages, then buy another battery. So, absorb time equals equation at the bottom. I won't go through this in detail with you, but you can go through it later if you choose to for your absorption time. Because absorption can be set, the absorption time can be basically set in one of two ways. We can either use time or we can use that current tapering as a kind of a trigger. We can set it for instance, 3 amps or 3% of my battery bank capacity. We call that value return amps or end amps in the case of a charge controller. But if you want to figure it out on time, the equation basically, the way that thing works here, you'll see down, there's kind of a long one, but it's the amp hours remaining divided by the charge rate, or actually half the charge rate. So you end up with kind of a number, a time number of approximately how, it's a good step point, and I would keep that rolling. So we'll go too deep in that. Making the charge settings. Okay, so here we have a graph. Again, I won't read all these to you, but really what this is all the voltages for all these different batteries. Where you got your REs, your GH, your OBZVs, and your flooded lead acid batteries. And so these are the voltages you're going to want to use. And so I think Mark wanted to add something here.
Yeah, I was just going to say this chart is available in an application note. So we have an application note on our website called battery charging for OutBack batteries. And so this chart is in there. We're not going to go through this chart right now, but you can follow along, pick out your battery and the setting, and reference the footnote if you need to. So
right, yeah. So now state of charge. Battery voltage is not a good indicator of state of charge. It only is if the batteries have been at rest for, I've heard people say 3 hours, I've heard people say 6, I've heard people say 24. But in essence, it's not a good indicator of state of charge. So what we have that's a really important product in our system is something called the FLEXnet DC. And I won't go deep into the theory here, but it's basically a shunt meter. So it measures the current going in and out of the batteries. I've heard them called Coulomb counters. And what it does is it measures and monitors current going in and out of the batteries. Now you first have to tell it, of course, how many amp hours it is to begin with, or else it won't know. It can't just guess. Any of these battery status meters cannot just be hooked up to a battery and tell you what the state of charge is. It has to follow it. So what we're going to want to set, when we set this up, the things that are important to set are here on the screen as our amp hour capacity. And you want to use the amp hour capacity for your system design. A frequent mistake people will make will be just to enter in the 20 amp hour rate, because that's what we always have done. Actually, if you can even look on YouTube, we have our sizing spreadsheet. It's also, well, it's going to be available very soon on our website. It's not right now. It'll calculate your SOC, I mean your amp out, your what's the word I'm looking for? Your C rate on your battery. So then we want to set a charged voltage. So we're going to set the capacity of the battery, and then we're going to set a charged, and I say that with a very specific D on the end. This is not a voltage you're going to achieve, it's a voltage you're going to measure. So in this case here, you're going to want to set that somewhere 0.2 or 0.4 below your charger setting. So in other words, if your battery manufacturer says to set an absorbed voltage of 57.6, we want to set our charged voltage at 57.2 possibly. The reason for that is we want to make darn sure that we get there, because this thing is going to want to reset every now and then, because all battery status meters have one flaw, and they can't, or there's a couple of flaws, but they can't measure self-discharge. So once in a while we need to basically reset the clock, and we reset it by getting up to a voltage, reaching our amp hour capacity, and also the next item down, which is set return amps. So return amps, remember I said that the current will taper in a lead acid battery. And if you set that return amps for 2 to 3% of the battery, you just use 3. It isn't rocket science here. And a little high is best. I will agree with that, because again, it's a value we want to achieve. So what we're really going to do is now the FLEXnet DC will say, okay, I've hit this charged voltage because I'm on my way to absorb. I've tapered down to this return amps value because the batteries are getting full at that point, and hit our charge factor. In other words, if I've got 100 amp hours out or 94 amp hours out, I got 100 amp hours in, then it'll say I've achieved my parameters, and it'll let you know that. And that is something you're going to want to make sure that you do every now and then, is to hit parameters to make this thing accurate. Again, we have a great tech note on this on the web as well. So charge termination control is a function that is used in the inverters and charge controllers to basically end the charging based on hitting our parameters. So in other words, if I'm charging with my grid or charging with my solar and I want it all to shut off as soon as I hit charge parameters, I can do that. So once the charge parameters are met, not only will the FLEXnet DC reset and tell you that it has achieved parameters, but the charge cycle will be terminated on all the OutBack devices. So it's depending how you want to charge your batteries, this could be a good thing. There's very many opinions on this, and that's one way to do it. So collecting information. I believe we're going to fill some of this out for you, but this is a great worksheet to use prior to going into setting up your battery. Again, this is one that people will often call tech support, inverter tech support for. Now, with OutBack batteries, you can call us, but of course, these numbers are actually in the tech note. They are in the manual for the batteries. They're even, a lot of it is on a sticker on the batteries. So our voltage, absorbed voltage and time. So I'm assuming that these are for the RE batteries, 57.6 volts for 2 hours. That's a good start. And that's based on the 14.4 numbers that you'll see on the battery. So in other words, if you look at a 12-volt battery, it'll say 14.4. You have a 48-volt system multiplied by 4. Float, 54.5 for 2 hours. A great starting point. And that comes from a 13.62, again, off the spec sheets. Refloat, this is at what point, and this is primarily an on-grid situation. What we do, and if we're in grid time mode, is we actually shut the charger off at the end of the absorb cycle instead of going into float and just constantly spending current to get the batteries in float. It'll shut the charger off until it goes down to this value. 50 volts is a great starting point. I've rarely seen any need for changing that. That's the default setting. Grid tied is going to be by default. So another thing to note here is if you're not wanting to sell back to the grid, you're going to want to disable that. The cell voltage. This is at what point in a battery backup grid tie system you're going to want to sell back to the grid down to. So in other words, during the day when the solar is up, the solar controller will be bringing the voltage up above that set point. The inverter will bring it back down by selling it back to the grid, and that's the voltage. Once the sun goes down, the batteries will drift. And they will drift, and hopefully they'll stay above that 50-volt refloat voltage. 52 volts is a good start. It's actually one I would recommend. It's what I would call somewhere between total rest voltage and lower than a charging voltage. So it's pretty much, in most cases, the most efficient number. Lowering that is not going to get you more energy back to the grid, by the way. The charger limit in amps. This is going to depend upon your battery capacity and off the spec sheet of your battery. So for instance, our RE battery, the 200RE, has a maximum charge rate per string of 53.4 amps DC. So you'd have to convert that back to AC amps, of course, because that's how you set it on the inverter. The default, I believe, is 30, depending on the model of the inverter. And here's that formula. So if we have 53.4 amps maximum on a 200RE, I multiply that by 2 for 2 strings, by 48 for 48 volt DC. I divide that by 0.8, by 85%, because battery-based inverters, or should I say battery-based inverter chargers, all are about 85% efficient in charger mode. I come up with 6,031 watts. If I divide that back by 240 volts, I end up with 25 amps AC. The default is 30 there. So in other words, if I had 2 strings of 200REs, that's what I would set it for. Next one, low battery cutout voltage. This one is, if we talk to 10 people, we're going to get 12 different answers, and I'm going to give you 2, maybe 3. The default setting is 42 volts. Many people think that's vastly low. And if you're using that as a floor that you hit often, then yes, I would agree it's vastly low. It would be damaging to your batteries to hit 42 volts. But the idea of low battery cutout is not to hit it all the time. For instance, in an off-grid system where you're going to be more prone to it, you're going to want to have your automatic gen start kick in before it. So you want to make sure that it isn't too high either. If you're in a battery backup situation where you lose power once a year and it's a critical application, 42 might be acceptable. So that number, again, if I was to have all of your opinions on this, you would all be right, depending on the application. But remember, if you are hitting that number, low battery cutout frequently, then you want to go back and look at your design or your usage or your production. So that's that one. And an example battery chart uses for 50% DOD, depending on the load. Again, one that's subject to many opinions. All of them wrong, all of them right. Battery cut-in voltage, this is where you're going to turn back on the inverter after hitting low battery cutout. And we don't want to have that too close. For an example, if I set the cut-in voltage for 47 volts, it would be cycling off and on, off and on, off and on. So I want to make sure we're charging. Amp hour capacity, that's going to be based on your usage, on your C rate of your batteries. You want to put that in correctly. In this case here, the correct value for this battery, I believe that's the 24-hour rate, is 181.4 times 2 strings is 363 amp hours. Battery setup charged voltage, that's going to be 0.4 less than your absorbed voltage that's recommended by your battery manufacturer, in this case us. Your setup charge return amps, 9 amps, that is probably 3%, we'll see, yes. About 2.5% of your battery capacity. So that's when the FLEXnet DC is going to say, okay, we've hit that number. And the charge factor, this is another one that's up for debate. 94% seems high to me. I would probably, to be on the safe side, set it at 85, but again, there's one for subject for opinions. So programming is fairly simple. The way I like to think about the way the mate is programmed is basically to show you all the different button pushes has some value, but you should get used to it. So if we think about this, kind of close your eyes and say, where would I want to hit? I want to go to a settings. And in this case here, we're going to be looking at an inverter setting. So I'm going to go to inverter. And there I'm just going to scroll around until I find something that looks like battery voltage. So if I see low battery, that's going to be where I set that low battery cutout and cut-in voltage. If I keep on going, I'm going to find battery charger. Pretty self-explanatory. Bulk are absorbed, float, refloat voltages and times. And then battery equalize. Now this is for typically for flooded lead acid batteries only. You don't want to, in the traditional sense, EQ or equalize a VRLA or quote sealed battery, but some battery manufacturers will in fact say to equalize just at a more like a absorbed type voltage.
Yeah, the OPZV batteries have an equalized cycle actually in certain ways that you use the battery. Yeah, so
every battery is different is the point here. And so, if you take this information and if you put in, basically somebody else's batteries, what people do, use their information. That's really what's key to all of this. Max charge rate, that's going to be the one, hopefully, in a perfect world, you'll never have to change this because your battery bank is large enough for your inverter or your system. But frequently, I'll see people who want to put in a battery backup system with a 10 kilowatt array and a 100 amp hour battery, which is to me not balanced. But you want to make sure that your charger limit is not set too high for your batteries. For example, ours, 53.4 amps per string, comes out actually to 12.5 amps AC per string. So if you have less than 3 strings of the RE battery, you're going to want to change that. It's a different value for the GH.
Yeah, I just want to add also, that's the maximum charge that we're calculating here. So if you're in like a float application and you have plenty of time to recharge your batteries, that'd probably be a good thing to do is to set that down much lower. And that way it's going to be less hard on your batteries. You're going to have more capacity. So if you don't need to charge them quickly, then lower is better.
Yeah, I agree. And also, if you just want to use less grid and prioritize more solar too. So there's other reasons you could do that. But again, for the maximum, there's a lot of reasons you would change that. FLEXnet DC, that's the battery monitor. All the settings, now this is not an inverter function. You're going to find this under battery monitor. And there's not too much here, so it's pretty straightforward. But your battery setup is where the bulk of your programming to be done. And there's your amp hours, capacity of your battery bank, your charged voltage. The time I would leave short. Return amps is that tapered current and charge factor of 94%, depending on the battery. So I would base, the thing is, these are the things that we're going to have to hit for it to reset itself. And so we want to make sure we can get there. If we don't reset ourselves, it's like a clock that's off a minute a day. Over time, it'll get less and less accurate, and then bad things happen. Generator starts at funny times, things like that. Here's another example of how to set the programming up, and there's one thing that, there is no such thing as a simple interface for a battery-based inverter. The Mate 3 and Mate 3S now is actually as good as it gets, and there's no question about it. It's pretty good, but it still is menu-driven. Scroll through menus and things like that, and a lot of times people don't like that. Look into our OpticsRE if you don't, because you can set all this up on web pages, really familiar interface. Here we have, you can see an example from what's called the device manager in OpticsRE. It's an online service, and we'll go into it. But you can see I've got all the values right there in front of me with slider bars, where I can just put in the numbers. It's a much easier way to set those voltages. So you may want to consider OpticsRE, which is, by the way, free. We've got webinars on that as well, I believe, and papers. So we got all the voltages, rebulk, refloat, all these things, float times, all those voltages. In the AC input, this is where you're going to set things like your charger AC input limit, which is how much it will draw from the grid or attempt to draw from the grid. And then we have our charger AC limit that we talked about in the last screen or two, what our maximum charge rate from the inverter is. So, commissioning, I'm going to hand it back to Mark. And
thanks, Roy. Appreciate that. So, battery commissioning. There's a couple of things that really need to be done. This is not, everything that may need to be done on a battery, commissioning batteries. But for sure, as a minimum, you want to measure and record each battery and cell, not just the string voltage, but you want to record the string voltage as well. And the reason is, in fact, on this very setup, we provided some backup power systems and for the trackers on a utility scale site. And there's only 2 strings of batteries per, but we did hundreds and hundreds of these batteries. And out of all those hundreds, I think we found like maybe 4 batteries that were bad. And the ones that we found were bad, you measured the string voltage and then measured 51.5. It's a 40-volt system. But one battery would read like 9 volts, and the one next to it would compensate with an extra charge and read 16 volts. So you'd have 2 batteries that are right next to each other. One's really low, the other one's really high. And then when you measure the string voltage, you say, oh, okay, 51.5, yeah, that's good. That's right where it should be. So it's really important that you measure each battery, each cell, put a little diagram, of your battery bank, and, record the voltage for each one. This is really important. So we're going to check these measurements against the manual specs for the type of initialization charge. Okay, and I encourage you to read each battery manual. They're on our website, so whichever OutBack battery you get, please read the manual. They're typically 8 to 12 pages with lots of diagrams and pages you can skip over. So the actual information you need is not on a lot of pages. Please read those manuals before you go out. So you're going to measure your individual batteries, and you're going to measure, what that string voltage is going to be, and it's going to tell you, what kind of charge to put on your battery. So you might just need like what we call freshening charge, which is like a 24-hour absorb. So instead of a 2-hour, you do like a 24-hour absorb. If it's below another lower level, like say 12.3 volts on a 12-volt battery, then you might want to do a 24-hour absorb and a 3 to 5 day float charge after that. One thing that's nice about OpticsRE is if you go in there and you find that, and you don't want to stay there for 24 hours or all week long, you can go back and you can put the absorb into a 24-hour absorb, and when that's done, you can look and see what the voltage is, and then you can go back and and revert it to its normal charge settings. So OpticsRE can help you, do some follow-up measurements if necessary. Okay, the other thing you want to check for is to make sure that the string current is close on both charge and discharge. Okay, if one string is more discharged than another, that could explain that. But also the thing that could be happening is if you have some contact resistance in your connection. And if you have a flooded lead acid battery, then you can use a hydrometer or a refractometer to measure the specific gravity. And in that case, the specific gravity will also show you, give an indication of what the state of charge is. Okay, post-charge load testing. So this is really important. Once you have the batteries charged up, turn on your loads. All the loads connected to the backup panel. Turn as many of those on as possible. It's a cycling load like a furnace or refrigerator. Open the door of the refrigerator, turn the heat up on the air conditioner or the heater. Get those loads going. And then measure for voltage drops across the batteries or cells. So again, you want to measure battery by battery or cell by cell. If you have multiple strings, then check and see, because once it's gone through a freshening charge, now everything should be evened up. You should see a fairly even charge and discharge, and you might see some discrepancy. The other thing too, that's one of the reasons why we have, when we do our cable runs from the battery bank to the inverter, or if you have a common DC bus, you want to make those cable lengths the same length so you don't get different voltage drops across. But anyway, any excessive voltage drops or string current amounts could easily indicate loose connections or bad batteries. You can measure those. You can measure those connections, or or you could also check with an infrared temperature probe. They have some fairly inexpensive infrared temperature probes. They come in handy like on a low panel as well. If you're trying to find a hot, sometimes you get a breaker that's got excessive harmonic currents, or it's the contacts are going bad, they'll heat up. Same thing on bus bars and anywhere where there's a connection with a lot of current going through it, it will show up as heat. Okay, so record any unusual findings that you come across. There's the SD memory card that comes with the Mate 3, and I highly recommend after you've done your programming, copy it to the config.xml file, which you can give it any name you want, but it'll give a .xml extension. I would save that onto your laptop, and I would keep that away for future reference, just in case somebody does come in and make some changes. If you have OpticsRE, there's an events log that will keep track, so if somebody does go in and make changes, the events log will record those changes. Enable system data logging on the Mate 3. So in the Mate 3, you have to enable the data logging. It won't happen automatically. It'll record those that log data on the memory card, and what it does, it records all the parameters, or almost all the parameters that would be relevant on every single device connected to the hub. So it really is a system-wide data logging. So if you do run into problems later, you can go through and check those logs, and you can see where, when things started to change. Take pictures of the system components and interconnections. That's really important, especially if later on you see some build-up or whatever on the sulfation or whatever on the bus bars or something, and you've taken a picture of it. Well, something has changed. Okay, so if you do see a low battery voltage, or if you do start to see that this white sulfation, whatever, come out of one of the battery terminals, and it's fairly young battery, be sure and file a warranty claim right away. And that's why it's also important to make these measurements, take these pictures, so if something changes, do want to file the warranty claim, because it is only against The warranty is for manufacturing defects only. It's not for system performance. And the warranties are limited in time as well. So that's why this last bullet here, make those measurements again in 3 months. Highly recommend you go out, because usually if there's a failure in the battery, that's going to happen with 3 months. And it might not necessarily be, a manufacturing defect in the battery, but it could be that the site owner is doing something they're not supposed to be doing, or maybe, there's loads connected that they didn't tell you about, or, there's all kinds of things that could all of a sudden, if the system performance is starting to go downhill and a battery's getting stressed from undercharging, overcharging, you want to do it in a fairly short amount of time before it's too late. If you come back, a year or two later and the batteries are trashed, there's really not a lot you can do about it at that point. Okay, just going to end with a couple of tips and precautions here, and then we'll go to the questions. Racking and disconnect solutions. One of the things that I've seen quite frequently, I've been to a number of field installations of OutBack equipment, and I'd say the majority of them do not have a disconnect between the battery bank and our inverter. And this is one of the reasons, like there's some safety issues for sure, like the battery bus bar in our plate, like in all of our load centers that you get if you have any system, pre-wired system, or buy any of our load centers, they're going to have a positive bus bar, and when you turn the inverter disconnects off, that bus bar is still hot. And it is possible, and I regret to tell you, I had a very exciting moment once when I managed to touch 12 gauge bare wire between that and the load center, and it was a very, very exciting moment. So definitely you want to have a way that you can disconnect these voltages. You'll see these are the battery racks from OutBack. Here's our 3-shelf and our 2-shelf. You notice that there's a disconnect for each string, these cabling that comes with each string. Here's the positive bus bar over here. There's a negative one on the other side. You can even attach shunts. Over here on the negative side, we have the pre-drilled holes, so you can actually attach shunts to the battery rack if you want to. And these are UL 1741. They come with clear FLEXnet safety covers. So they're really, by the time you add all that up, if you were to put together your own battery rack, unless you're really going to go cheap and not put disconnects and wood box or whatever, if you come up with anything comparable to this, or look at our competitors, this is very competitive, and it's really worth doing. Okay, on bigger systems, it's almost a must. There's just too much energy that you can't just allow to combine, especially if you see these bus bars here. It's a very common scheme. We also have for big systems, we have an application note, by the way, on doing both AC and DC busing. Our DC busing suggestion is a little bit different than this one. But you notice at the top of the battery bank, there are some disconnects that are up there. Here's another company, this EEEUSA.com. They have a lot of different really nice solutions. They're a bit spendy. I'll say they're not cheap, but we're getting into this size of battery bank. You're investing tens of thousands of dollars anyway, so you might as well protect your investment. Not to mention the safety factor. This is a site I was at a private home. I had 2 strings of the 3000 OPZ-V batteries that had very huge battery bank, 6,000 amp hours. You can see these the OPZ-V batteries, they come with these little string cables here, like these busing cables. So these are 2-volt cells, and there's 3 per battery, if you will. And so these little cables come with it. And also with the OPZ-V, you can get an optional disconnect. Now, the installer made up this busing scheme here for for the disconnect to mount onto. So this is not something sold by OutBack, but this is what they came up with, and here's the little disconnect switch here. Okay, and lastly, I want to talk about state of charge. Roy touched on this earlier. It's probably one of the things that we get called about, and you probably get called about a lot, and that's when the battery status light here goes from green past the 3 yellows down to the one here bottom that turns on red. The red light comes on. Usually this happens for a couple reasons. One is when the system is commissioned, you want to unplug the FNDC, that's what we call our battery monitor, the FNDC cable from the hub. So that'll take away the power from it, and we plug it back in. That'll give it the 100% reference. So when you've done all your refreshing charges, you're sure the battery bank is up and running, you know, it's at 51.5 or higher for a 40-volt system, unplug that and plug it back in. That'll set it to the beginning. Now, the other thing that can happen is this first bullet up here, consecutive partial charges will accumulate errors with each charge. Okay, so it's with each partial charge, because the battery charge factor adds something. So when we measure the amps out and the amps back in, the amps back in has to equal the amps out plus the BCF, which is the battery efficiency. Okay, so it's really important when that happens. Now, once the system's up and running, there's two things that will reset the FNDC, the SOC to 100%. One is when charge parameters are met. That's the charged voltage that Roy was talking about, and the time, and the return amps. So when those three parameters are met, then it'll reset to 100% SOC. Also, when the amps back in equals the amps that went out, plus the BCF, which is battery charge efficiency, that will also set SOC to 100%. Okay, so fully charge batteries regularly, that'll keep the SOC up there. So if you're doing full charges, even if the SOC gets off through this partial charging, once you do a complete full charge, it should come up and reset itself. If it doesn't, then you can just have your customer because you can look at on OpticsRE, you can look remotely and say, hey, the battery bank's 51 volts. You know that red light should be coming on. You can just tell your user, hey, unplug that little, RJ45 connector from the hub, plug it back in. That'll reset it to 100%. Also, there's a number, I believe it's under the battery monitor soft key on the Mate 3 system controller, called days since charge parameters met. So these charge parameters up here, it monitors how many days it's been since they've been met. So if you're saying a high number, then something's not going right in the system, and you can try and figure out why that is. One thing I've seen that's fairly common too is on a new system, sometimes I think the default only the A shunt or the A and B shunt are turned on. So if you're using the C shunt for something, you'll need to make sure that it's turned on. So it's another thing under the setup. Make sure all your shunts that you're using are turned on, and the ones you aren't using are turned off, because they will pick up noise, because we're just measuring like 1/10 of a millivolt as 1 amp. So they will pick up some noise that could give you some false readings. So make sure that the shunts you're using are enabled, the shunts you aren't using are disabled. And again, the bottom line is, hey, if you got 51 volts on your battery, 51 volts in your battery bank, and the red light's on, well, guess what? Just reset your FNDC and you should be good to go. Okay, and then the temperature corrected charging. This sensor comes with every inverter and charge controller. Please use it. Unless it's going to be in a battery room at room temperature all the time, you definitely want to have this. If you get any temperature fluctuations, you definitely want to plug in and set this. Typically, you will put that in the middle of the battery bank, and you should be good to go. Okay, so that's all we have. We're going to go to questions right now.
Well, there won't be any questions on batteries. Everything's so simple.
So we'll go to the top. Okay, so which is better for battery bank management, enhancing battery bank life, SOC or voltage? Well, that's a tough question to answer, but I'd say if you are doing regular charging on your batteries and you reset it to 100% properly the first time, and you have the right battery charge factor in, you've got all your charge parameters are set right, SLC can be used fairly reliably, but it has to be fully charged on a regular basis. If you're doing partial charges, voltage could be, and in the manuals, since on some of our batteries, they will equate a voltage to an SOC. However, as the battery ages, that will definitely change. And once you start cycling a battery at a given site, it's going to be hard to know exactly, but kind of one general rule of thumb I use, a new battery under load is about 46 volts at 50% SOC. And but that's really sort of, that's really kind of I think so. Somebody says we've lost some audio. I don't think that's on our end. Recording of the webinar, yeah, we will probably post this one. We're going to do another one on Friday, so we'll either post.
They will be on YouTube, I know. I know.
Yeah, so other ones. We'll post one of these, either the one from today or the one on Friday to YouTube, our YouTube channel.
Battery amp hour. The battery amp hours on FLEXnet DC is supposed to be set at what? So it's going to be the amp hour capacity of your batteries. And historically, I think people have always just kind of, we used to always say in renewables, and we use the 20-hour rate, because some of the battery status meters actually will use Puchert's theorem in their calculations. Ours does not. So there is a webinar out on our the conglomeration that we have in App Engineering. It's a spreadsheet. And that spreadsheet will calculate your battery capacity needs. And it'll also tell you at which C rate that you'll be using your battery at. So the one you want to put in there on amp hour capacity is the appropriate C rate for your application. As an example, if you have a given set of battery that's sized properly, in an off-grid situation, for instance, with 2 days of autonomy and at a 50% depth of discharge, that turns out to be a C100 rate, or actually C96. And that's what we list our batteries at. All batteries have a nameplate listing. It doesn't, just because one company says 100 hour and the other says 20, doesn't mean one's being dishonest. So I would say put it at the appropriate one. If you watch the webinar on the sizing spreadsheet, that'll be explained more. And that's up on the web right now, I know.
Okay. I'll go ahead and take this next one. Is it okay to put cell voltage at 54.5 volts and slightly raise float voltage, which effectively keeps the batteries in float while selling? So essentially, you could do that, but it's really not necessary. So what happens is there's also a grid tie setting on the charge controller as well, and that'll put that at a higher voltage. But the cell voltage itself, it's going to try and maintain a low voltage. And by doing that, by putting the inverter at a low voltage and the charge controller at a higher voltage, that difference in voltage is what makes the current flow down, okay? So setting the cell voltage up is not really an advantage. So we're going to try and hold 52, but if the charge controller is trying to put out 54 volts of float voltage, or grid type cell will actually try and put out 57, that's going to make it sell harder. So I would say, typically 52, 52.5 is going to.
I would agree with that, and I would say that if you did put it up there, it would not get you any more energy or less energy back to the grid. It would just, it would take more energy to maintain that, so it would be less efficient. Okay.
So I'm going to take this next one too, because I had some experience with this. So are you going to publish an app note for charge settings to maximize NC life if using off-grid? So we had done some experiments with that, and I'm not going to go into all the details now, but it's kind of like when we'd go up to like we experiment with going up to like just hitting the absorb cycle, so we're like 80 to 90%. And then we would let go, but then we had to maintain a cell voltage, and that would immediately discharge the battery. So anyway, we talked with our supplier of the batteries, and there isn't really a good charge settings to put in there right now, the way that our system is set up. So basically, the best thing is to fit the battery to the application. So if you're in a cycling application, like an off-grid system, or if you're doing ancillary services, like let's say you live in California or some other place that has time of use charges, you say, okay, I'm going Monday through Friday, I'm going to go off-grid from 4 to 8. And so that's going to cycle the battery. So I would say go with, we're not going to do with settings, but just take, if you're in partial, if you're doing a lot of partial charging, it's going to enhance the number of cycles. So it's kind of like a catch as catch can sort of a scenario.
Well, next one is a long one. Okay, my system is both solar and generator. The solar capacity is limited. Okay, so generators run every day. The Mate 3 can run the generator when there's a heavy load. I have boy. Oh, okay. I'm kind of reading it. Yeah, I guess you can't. You guys can't read this. I'm reading it too quietly. So, okay, my system has both solar and generator. The solar capacity is limited, so generators run about every day. Okay, so you're basically cycle charging. That's fine. The Mate 3 can run the generator when there's a heavy load. Yes, you have it set for load start. I have such a load that runs about 20 minutes. Is it better to use gen load start, which would create more charge cycles, or just use the normal charging cycle? Okay, so basically, I'll kind of summarize that. Your primary charging source is your generator, and in that case, in my opinion, it's best to always just use either SOC or voltage. Basically, do it on whatever you're doing it for the batteries, but you're using it also for this load start. I think it depends how long that runs. If you can get by without using the load start and just depend upon it depends how big that load is. Yeah, that might be one for tech. That might be one to take a next step further.
I just want to add one thing. The very last part was it creates more cycles but lowers the depth of discharge. So, this is one of those things when you look at the life cycle versus depth of discharge thing. If you're going to do more shallow cycling, or you do more cycling, but you're going to do it shallower, then yeah, it's that's the trade-off there. So yeah, you're going to get more cycles. If you're discharging it less, then you're going to get more cycles of life out of your battery. So yeah, it's kind of to tell you that hey, yeah, if you do this, you're going to get 2 more years out of your battery. I'm not sure we can make that determination. So the next question. If the nanocarbon is better at PSOC, but also at cycling application, what is definition of cycle? As an example, a system that cycles every day but has adequate PV to fully charge every day, even in partial sun. Not sure I fully understand the question, but if it really gets down to how deep you're going to discharge, right? And the worst case scenario is an NC battery is going to be the same cycle life as an RE battery, okay? But partial charging on an RE battery is somewhat of a detriment, okay? On a nanocarbon battery, it's not. The other thing we need to mention here also, if you are going to do significant partial charging on a nanocarbon, you will need to do a full absorb, every month, like at least every 30 days. So if you are using a nanocarbon in a PSOC state, like every day, and you're never really fully charging it, or maybe it just goes up and kisses the absorb voltage and stops, you do definitely want to do a full, like 2 or 3 hour absorb once a month.
Okay, so if slower charge rate increases capacity, how does that affect the absorb time? It'd be a longer absorb time. And you can go back to, remember that formula that we had back there. It was basically, it was the amp hours remaining in the battery, and it was the charge rate times a half. So you would increase your time by decreasing your charge rate if you did that. Okay, nickel iron, yeah, quite a bit. I would say follow. Oh, okay. I'm sorry. I'm kind of going. I'm assuming everybody's reading these. I'm making a mistake there. So have you ever worked with nickel iron batteries? The answer is yes. Follow their recommendations. We don't make any. I mean, that's really comes down to that.
Okay, the one question is the OutBack catalog and some spec sheets don't talk much about OPZ. What are typical applications? One thing that's kind of interesting about the OPZ is it has a long float life and lots of cycles. And so you say, well, why wouldn't everybody want that battery? Well, it's basically it's a price thing. The OPZ-V batteries are pretty expensive, but there's not a lot of downside to it. Although I did see, I think in certain partial charge applications, they do recommend doing an equalization charge, which is something you never do with an AGM battery. But some gel batteries, under certain operating conditions, do recommend doing an equalization. So there could be some extra maintenance that you might want to do. But the OPZ battery is a great operative battery. I've seen them in some really big, like, well-to-do homes in Cabo, San Lucas, and other places like that. And so they're a great battery. It's just, it's a money thing. I think
Is it correct to say that their availability is more Europe-centric than here as well?
No, their availability is just that there's some long lead times. Okay, so if you're gonna use those batteries, give yourself plenty of time to receive them. Will slides be available? Yes, we will make the slide available. Also, the application note that kind of this webinar was based on is on the website now.
Rebulk was not discussed. Good catch there. You're right. So in refloat basically says, okay, now I've hit this level. Say we'll call it 50 volts, and now we will go back into float. And how long will we stay in float? We will stay there for the float time period that we have programmed. Rebulk basically means and this is only going to happen if we lose grid or if this is an off-grid situation, right? It wouldn't happen if you're connected to the grid during that. So if you get below that rebulk setting, there's a timer, and I don't know exactly the algorithm, but it might be 1 for 1. In other words, for every minute I'm below the rebulk setting, then when the grid comes back, I will spend 1 minute above the at bulk. So it basically, I call it rebulk protection. So instead of going into a full absorb cycle every time, it makes an adjustment on how long it stays in bulk, or absorb, I should say, upon returning to it, if it gets down there. It's a little bit more complex than just the reflow. So there's a timer there. I think it's 1 to 1. I could be wrong on that.
There's another question here that come up. It says most OutBack information shows 50% depth of discharge for cycles, etc., but I don't see preferred depth of discharge. Will 50% depth of discharge cycling meet warranty requirements? And I will say it will now. We had, we saw that we were recommending 50% depth of discharge and as a kind of the same thing, and then our warranty document said 40%. So that has been changed just like recently to reflect a 50% depth of discharge. Although I will say, in terms of cycling, any performance issue is not covered under a warranty. It's not a warrantable thing. Okay, so anything with cycle life or whatever, because the way once a battery gets on site, it's going to be used differently, and there's no way the local temperatures, the temperature cycling, the way it's going to be charged and discharged. Every site's going to be completely different, and there's no way that we can possibly know what that is. We test our batteries, or our manufacturers typically do it at a C5 rate, and that's how they base their data on. Again, the 50% depth of discharge just means that if you're doing like really deep discharging regularly and your battery and they're not charged properly, then might not be warrantable. But if you suspect you have a warranty failure, that and especially if the whole battery bank goes bad, that's not a manufacturing defect. I mean, you just don't see those kind of batteries. But if you go through and you after a few months, 6 months or whatever, within the warranty period, and all of a sudden one battery is reading 8 volts or 9 volts or something, and everything else is okay, then yeah, that's probably warrantable, and they can do an autopsy on the battery, and they can see if it's been a defect or not. So.
And I would add that as far as a recommended, I wouldn't think that we would do a recommended. What I would do, and I've actually done this exercise, is I've taken an example battery, and the one I used was a 200RE, and I figured out the cycle cost. And the way I did that, you can do the math yourself, but basically it's at a 50% depth of discharge, which you can calculate how much that is for a battery, based on voltage times, amp hours. At a 50% depth of discharge, you get 1,800 cycles. Now, if I multiply that 1,800 cycles by the number of kilowatt hours, I should say, of that cycle, I can get a total number of kilowatt hours. And I can do that at different levels. I can do it at 50, I can do it at 80, I can do it at 20, for an example. What I've come up with is that 50 is the sweet spot as far as not spending excessive money up front and getting the life out of the battery. If you're only cycling that battery 20%, for example, you save a little bit. It's a little bit less per kilowatt hour, but will it last? I mean, if you cut your cycle life down to where it would last for 50 years, no, it won't. So you have to find that sweet spot, and that's one, and it all comes down to your application. So I would say that we wouldn't recommend the perfect one.
Okay, I think that pretty much wraps it up. We're at the end of our questions. Thank you very much for attending. And
very handsome audience they are.
Yes, I was going to say the same.
Yeah.
And this will be repeated at 10 a.m. this Friday if you wanted to recommend this to anybody. And it will eventually be up on the...
It's on the YouTube channel.
OutBack has a YouTube channel, and it will wind up there eventually. So again, thank you everybody, and have a great day.